Okay, so for problem 6 here, we are supposed to find out the location of the center mass as well as the central mass moment inertia and the compo for the composite object. Well, conceptually, we know that the center mass mass moment inertia, it is the concept that very similar to the previous problem, right? And what we need to do is to replace the geometry or the dimension of the object, that is actually area, with the corresponding mass, right? And everything else will be pretty similar here. But again, since it is a composite object, we need to divide it into regular objects, right? So okay, so now we can go ahead to approach that first to determine the location of the center mass first. So for this composite object, we see that it is composed of okay, a square plate. That is our part one, and a circular plate, part two. Okay, please note that it is a circular plate. It is not a sphere. Okay, so the third part, it is a rod, right? Okay, so the third part here is a rod. Okay, given that information, so now how are we going to evaluate the location of the center of mass here? Okay, so x3 equals to. Okay, so now it is a concept that very similar to the previous problem to evaluate the location of the centroid. So now it is a weighted average of the center of mass of each part. But now the weight changes to mass. Okay, so it will be summation of the mass of each part times the corresponding center of mass of each part, right? So probably you see that the notation here we have is xg, which is actually the center of gravity. But typically for the problem that we deal with, the center of gravity is consistent with the center of mass. Since we have a gravitational acceleration is typically a constant we within the body of the object. Okay, and divided by total mass here. Okay, so now we are going to go through the parts one by one. So for our part one here, what is the mass of that? It's the 3 kilograms, right? It is 3 kilogram here. Okay. And what is the x coordinate of the center of mass of the first part? Well, typically, so if the problem didn't tell us the for example the function of the density of the object, we typically assume that it's a homogeneous here, meaning that the center of mass is at the very center or the centroid of the shape. Now here it is actually at the centroid of the square, right? And the x coordinate central square is a hub. It is located at a hub of the at a hub of its space from from its head, right? So it is actually so it is actually so the base here equals to 2, right? And divided by 2. Okay. So actually it is located as located at x equals to 1 meter here, right? Okay. So plus so the mass of the second part is 2, right? Times where is the location of the where is the location of the center of mass of the circular plate? It is at the very center of the circle, right? So its x coordinate equals to it equals to the length of side of the square, right? which is actually 2 plus the radius of that circular plate, which is actually 1, right? Okay, and then our rod here, so it is so the mass equals to 6, right? And where is the location of the where is the location of the central mass of the rod? So it is actually again it is at the very middle of the rod, right? So it is a meter from so it is a 1 meter from each end. Then the x coordinate of that will be, so 2, it is the size of the side of the square here, plus 2, it is the diameter of the circular plate here. Then plus 1, it is the distance from the end to the centroid of the rod here, right? It is actually the x coordinate of the center of mass of the rod. Okay, then divided by the total mass, right? So it is the total mass here. Okay, so now if you evaluate that, you're going to see that it equals to, so the numerator here is 3 times 1 plus 2 times 3 plus 6 times 5, okay, divided by the total mass here. It is actually 3.55, okay, so it is a meter here. Okay, so actually, if we denote that, we are going to see that it is roughly here, right? Okay. So after you evaluate that, and you can think about that if this result makes sense to you. At least we would expect the center of mass, it will be within the, so actually it will be since it is a weighted average of that, right? It will drift towards a little bit more to the part that has a larger mass, right? Okay, so now we have the location of the center of mass of that. We can proceed to the second part. So the second part requires to determine the central dome mass moment inertia of the composite area of the composite object. And how are we going to evaluate that? Well, so it will be very similar to the previous question, right? So I mean the question, so for that requires to determine the moment of inertia, right? So again, we're going to use the parallel x theorem, but it is a parallel x theorem for mass moment inertia here. So we know that Hg equals to, so it equals to summation of the mass moment inertia, of each part, right? About the xg. So it is actually, and for each part, it equals to, according to parallel x theorem. So it equals to the central mass moment inertia, right? Central mass moment inertia of each part, denoted as I, plus, okay, now it is a mass of each part times the distance between the center mass of each part to the axis or the point that we would like to evaluate the mass moment inertia, right? The square of that. Okay. Now for part 1 square here. So the central mass moment inertia equals to, okay, that information is in our appendix. So if you go to the appendix, you see that, well, actually it is on the almost the last page here. We have the central dome mass moment inertia equals to 1/12 times the total mass times the summation of squares of the two sides, right? Okay. So it is actually 1/12 times the mass of the square, which is actually 3, times the summation of squares of the two sides, and both are actually 2 since it is square, right? And then plus the total mass times the square of the distance between the center mass of the square to the center mass of the entire object, right? So the center mass of the square is located as in the previous question we've already calculated that it is a half of the head of the side. Okay, so it is a minus here, meaning that it's the difference between the center mass of the square to the center mass of the object, which is actually located as 3.55, right? We calculate that and the square of that. This is actually the mass moment inertia of the first part. Okay, so plus second part. Second part is a circular plate. Please note again, it is not a it is not a sphere. Okay, it is circular plate. So for the circular plate, again we can go to the appendix, and we see that the circular plate here is so it is 1/2 times the mass times the square of the radius, right? Okay, so now it is a 1/2 times the mass, which is actually 2 kilogram. Okay, and then square of the radius, and radius is actually 1, right? Okay, okay, so now plus the mass of the circular plate times the square of the distance between the centroid of the actually it's the center mass of the circular plate to the center mass of the entire object. Okay, so the center mass of the circular plate, it is 2 plus 1 from the previous question. Okay, so it's the difference it is the difference between that to the center of mass of the entire of the entire object. Okay, so plus now we comes to the part 3, the road, right? So it is so the centroid so the central mass moment inertia of the road, which equals to, okay, in our appendix it is saying that it's a 1/12 times the mass times the square of the length, right? Well, if you see that, you are going to see that it is very similar to the central mass moment inertia of the rectangular plate, right? So as long as you have one dimension tends to equals to 0, right? You're going to see that it's actually simplified. It is it becomes it becomes the formula of thin road. Okay, so it is from the appendix we have it is 1/12 times the mass, which is actually 6, times the square of the length, which is actually 2. Okay, plus the total mass times the square of the distance between the centroid of the rod, which is actually 2 plus 2 plus 1 from the previous question, minus the the coordinate of the centroid of the entire object. Okay, so now it is the summation of the mass moment inertia of all the 3 parts. Okay, and we can go ahead to evaluate that. So for the first part, it's 1 divided by 12 times 3 times summation of squares of the two sides. Okay, and then parallel x theorem, we have 3 times 3 is the mass of the first part times the square of how much the x is so actually it is a square of the distance between the central center mass of each part to the center mass of the object, and we have the first part equals 21.5. So, and for the second part, it is 1/2, a half of okay, of the mass times the square of the radius, which is actually 1, then times the mass times the square of the distance between the centroid of the part and the centroid of the entire object, right? It is actually that actually equals to 1.61. Okay, so now if you look at the second part, my matter appears to be too small, right? The reason is because the location, actually the mass of the second part, it is much more closer to the axis or the point about which we are evaluating the mass moment inertia, or this centroid or the center mass of the entire object. The more closer it is to the axis that we are evaluating the mass moment inertia, the smaller it is. Okay, so and then comes to the third part. It is 1/12 times 6 times the square of. Okay, so it is a square of the length plus it is again the parallel x theorem, right? Okay, we have it equals to 14 14 point uh 6 6 and 2, right? Okay, if we take the summation of that, it's actually equals to 37.74, right? Okay, so now again, we can see that the mass moment inertia of the rod, it is also kind of significantly larger compared with the circular plate, right? Again, it is also because of it is so the mass of rod, it is relatively far from the of the centroid of the entire object or the location about which we are evaluating the mass moment inertia. Well, it is also because that the mass of the rod, it is larger here. Okay, this is actually the sixth problem. So the sixth problem examines if we can evaluate the center mass and the mass moment inertia of the composite object. So for the location of the center mass, we see that it is very similar to evaluating the centroid of a composite area, right? It is a weighted average of the center mass of each part. So and when it comes to the evaluation of mass moment inertia of the composite object, again, we're going to use parallel x theorem. But now for the version of parallel x theorem for mass moment inertia, so it is so please note that here it is actually the mass of each part. Okay, okay. Okay, and it also requires us to have the central mass moment inertia of each part of the object. So that can be found in the appendix. Okay, so that will give us all the information to solve the problem here.